Okay, so for those who don't know me, I'm Mike Jones. I'm a postdoc at University of Arizona. I foolishly volunteered to present all of the galaxy and cosmology things, so I'm going to be going through all three sessions. Roughly, our sessions kind of broke down into the following categories. So the first one was basically discussing breakthrough potential. The second one was more about science questions and challenges. And the third was about the tools that we'll need to address those challenges. Um, and just sort of as a clarifier, our group was mostly made up of observers, and we also had a strong bias towards galaxies rather than cosmology. So just keep in mind that everything I say is kind of through that lens. Um, so we started off just asking the group uh, what rare gems are going to revolutionize our understanding of galaxies and cosmology. Um, and so here's the word cloud that we came up with. You can see the biggest thing there is weird early galaxies, so these massive galaxies that form very early on in the universe. There's also a uh, big icon for dwarf galaxies. So dwarf galaxies have a lot of potential to help our understanding of galaxy formation, dark matter, and reionization. And then one of the big things I think that we agreed on is that one of the things that these big surveys are going to allow us to do is to really look at short-lived states where maybe galaxies are transitioning from one evolutionary path to another. And those are the kind of things that maybe most galaxies go through that, but they're very short-lived, so it's difficult to catch. And then, of course, there's the unknown unknowns that we shouldn't forget about. But we did sort of discuss this, and one of the important points is that when you find weird things, it's very important to talk to an expert that has a lot of domain-specific knowledge, because what may look weird to you might be something that somebody else looks at every day. So we need to be a little careful with those as well. Oh no, aliens is definitely, it was a joke, I think. It is true. It would be a revolutionary discovery. I think when that came up, I quibbled whether that counted as a discovery in galaxies and cosmology, though. I'm not sure it counts. Okay. Okay, so the next question we asked was, will there be any big discoveries in galaxy and cosmology in the next decade? We didn't define big, but as you can see, a third of our group said no. So this is kind of a tough crowd. For example, when we were talking about the big early galaxies that we've seen with JWST, some people were very excited about those, and other people was like, meh, cosmology is probably fine. We just don't know how galaxies form. So it was kind of a tough crowd. But the people that said no, I think generally their point was that usually most progress is quite incremental. Maybe this is more true for galaxies science than cosmology. And then, maybe it's more true for galaxies than cosmology. And the people that said yes, they're kind of motivated by the fact that we still have no idea what dark matter is, even though it's in everything. And then we have things like the Hubble tension. There's this sort of tentative DESI result. Maybe there's some evolution in dark energy. And then also that new technologies generally lead to new discoveries that you're not expecting. So that was kind of the breakdown of why people said these. Then we discussed how machine learning and AI can be used to enable new discoveries. And these are kind of the things that we came up with. So generally, this is sort of focusing on replacing sort of arduous work that people are not very good at, or maybe it's impossible for people to do, like looking at things in really high dimensions. And so it's using machine learning to really replace a lot of that work that's very difficult for people to do themselves. And then look for things like gaps in high dimensional spaces where interesting things might be happening. And I think one of the key takeaway points from this discussion was that machine learning is a tool. It's a very useful tool, but discoveries are made by people. And so we should keep that in mind. We should use this tool and use it to its full potential, but it's still people that are going to make the discoveries. then moving on to the second session, so we asked our group whether we feel prepared for the LSST era, and as you can see, the like quite a large majority said no, and this kind of centered on a few points. So first of all, with this enormous data set, a lot of people didn't feel that they were prepared to ask the most interesting science questions with this completely enormous data set that you can't wrap your head around. And then there's also going to be a shift to having to work in like a completely cloud-based environment, and making that shift is potentially going to involve a lot of additional work for people that are already totally saturated. So that's something that we don't really know, didn't really discuss how to solve that, but that's a concern for people. And then the people that said yes, they're saying, really we actually have the foundations of a lot of the tools we need. We just need to scale them up, basically, so that we can handle the big data era. And another key point was that some other communities, for example, in radio astronomy, have kind of already gone through this transition. So in terms of sort of data volume, radio astronomy is several years ahead of this community. And they made it through this transition, and so it is possible. And then the final point here is just that ultimately, we're all very curious people, and so this is going to be a bit of a challenge to shift to a new working style, asking different types of questions with different data sets. But we're all very curious, and I'm sure that we can do this if we put our minds to it. Okay. Then I guess, yeah, we asked sort of, this is about the challenges. So, oh, sorry, not challenges yet, my mistake. This is more about the science questions. So what's like the problem, the science problem that we should focus on as a community? Unsurprisingly, we didn't decide on one single problem in all of Galaxies and Cosmology, but there are kind of three broad themes, I think. So sort of talking about galaxies, their ecosystems, the black holes and their general evolution with their surroundings. Then also creating a complete sample, or a complete as possible sample, of low mass galaxies in the local volume. And then finally, sort of more cosmology questions like what is dark energy and dark matter, and how can we resolve Hubble tension? And then we asked about what challenges are we going to face when we try to address these questions. And I think something that kept coming up is basically survey uniformity. So what are you going to do about galactic cirrus, scattered light, having good background subtraction that's suitable for all your science cases, things like that. And then, oh yeah, another big one was that we're going to need to have artificial source injection at some level. And it's not really clear about exactly how and where that will happen. And then, as with anything else, there's going to be a learning curve to doing new science with a new telescope. That's just how things work. And then again, this is kind of, I think, carrying on from the point of the last session. If possible, we would like to avoid an escalation of the effort and competition along with the escalation in the data volume. Then, yeah, so the last question I think in this session was, are rare gems actually important? So I like to, I made this banner at the bottom, so I like to think of this question as, rather than rare gems in big data, it's rare gems versus big data. So I think the point here was that when people thought back to SDSS, that many of the biggest papers from SDSS are about like galaxy scaling relations and colors of galaxies and things that come from many, many thousands of sources. They're not from rare gems. Yeah, you're not necessarily going to convince somebody that their theory is wrong or whatever by having one object, because you can usually explain away one object if you're willing to wave your hand a bit. But it is those rare gems that often motivate deeper follow-up, expanding whatever observing program. So they are still very important for that reason. And the comment that was made at the end of this discussion was more money has been made from mining coal than from mining diamonds. And so I tried to Google this to see if this is actually true. I went down a bit of a Google rabbit hole. I didn't get to the answer. I found like a Great Depression era New York Times article about the price of coal, gold, and diamonds, but yeah, it didn't answer my question. So this remains an unsubstantiated claim, but the fact that it's even possible, I think, is the point. Okay, so in the third session, as I said, we focus more on tools. So first question was just what are the tools that we're going to need to address the challenges that we have? And one of the first points there was that we have a tendency to kind of use the tools that we know rather than finding or inventing the right tool for the task that's best suited to the task. So we need to think about what tools we need in order to construct the tools that we actually want. And then another big point was that all of our galaxy science and certainly all the cosmology as well is going to need comparison to simulations, and you might need various different baryonic physics, for example, that go into those simulations in order to understand what's happening with your galaxies. And so that's kind of a big ask, but it's something that we probably need. And then, oh yeah, we may also need the potential to reprocess at least some of the raw data, depending on, if there's something that happens in the pipeline that's bad for your science, for example, that's something we might need to reprocess. So I kind of summarized this with 2 points. So the dream is to have a completely modular workflow where you can imagine having say in your science platform, you could just have like different tools that you're going to use for background subtraction, your photometry, your cross matching or something, and you have different tools and you can literally just like drag and drop them into your pipeline and press go. So that's the dream. And then the other part of the dream part 2 is to have like say a gigaparsec cube full hydro simulation suite with varied baryonic physics. So that's also a very big ask that's probably not realistic. But maybe there are some ways that we can approximate this, perhaps with applying machine learning to like interpolate between different simulation models, or for example, someone was pointing out that I think it was Euclid and Roman are planning to share a simulation suite so they don't have to reproduce effort, because you can use the same simulations, you just need to create different sort of visualizations of those simulations for the two surveys. So there's maybe some progress in that direction. Then the next question in the third session was a kind of a big one, like how are we going to decide what we follow up and what we don't follow up? So I guess there was kind of consensus that ultimately this is going to have to rely on some sort of cost-benefit analysis, and that probably that's going to come down to the tax of individual observatories in a lot of cases, but maybe we also want to think about some community priorities. We didn't come up with community priorities in this discussion, but that was sort of tabled as something we might want to think about doing, and maybe like the decadal review is a good place to look for those priorities. In terms of follow-up of rare gem candidates, we kind of agreed that those are probably best suited to things like spare fiber programs on for DESI, for example, or SNAP observations for HST. Where it doesn't matter if you don't get all of your sample, but you can still find very interesting things. But it's kind of less expensive, say, for the observatories to do those kind of observations. And then the final point was for small telescopes. So although most of the follow-up we want is going to be like space-based imaging or deep spectra, there is still some targets where you can have bright objects that you want spectra of. And so small telescopes are a very useful tool for that. And one of the problems of having lots of small telescopes is the operating costs. So maybe these can be reduced by, for example, dedicating a telescope to a particular, like a single observing mode, and making it fully robotic. And then I think this is the last slide on session 3. So our final question was talking about what data sets we're going to combine and where's this going to happen. So generally we agreed sort of these things in bold, they're kind of the obvious choices of the kinds of things we're going to want to combine. And at a catalog level, you can probably do this just on the science platform. But for imaging, that's going to be more difficult. And one of the problems in both of those cases is going to be different sort of protocols between different surveys. But maybe we can learn from example from the Virtual Observatory or CDS that have kind of addressed this sort of protocols problem to some extent. And then, yeah, a big issue is just going to be data access rights with trying to combine these things. And it's possible for some of them, we're just going to have to wait for public data releases and hope that they have all of the information that we actually need to do the science. And then that's maybe kind of a negative note to end on. So I just wanted to put up this sort of overall summary slide. We were definitely very excited for the LSST era and all the science we can do, but there are still some challenges that we're going to have to address. Rare gems are very important for motivating our curiosity and motivating follow-up, but it's also very important to look at the coal as well. Yeah, we expect a lot of progress in galaxy evolution to be incremental, but that's still extremely important. And for cosmology, there's maybe more chance of a bigger shift. And machine learning is an essential tool that we should make use of, but ultimately discoveries come from people. Okay, thanks.